Chapter 7 ERA and the Boeing 757 ecoDemonstrator. NASA contracted Boeing to test two ERA technologies on the 757 ecoDemonstrator. The first of these focused on active flow control, AFC, to improve airflow over the rudder and maximize its aerodynamic efficiency. Preliminary research indicated that AFC could improve aerodynamic efficiency and potentially allow for the use of smaller vertical tails on future airplanes. NASA also tested non-stick coatings on the 757's right wing to reduce drag from insect residue. This would enable more laminar flow by smoothing the airflow on the surface of the wing. With the exception of Boeing's proprietary technology, all NASA knowledge gained in collaboration with Boeing from ecoDemonstrator research became publicly available to benefit the aviation industry. Both technologies are designed to improve the airflow over the surface and ultimately reduce drag, said Fay Collier. Increased drag means increased fuel consumption time, which results in more pollutants in the atmosphere. The 757 ecoDemonstrator was a highly modified Boeing airliner that served as a test bed for a variety of technologies. The project was built upon previous work by Boeing and various government and private partners to accelerate and leverage new technologies to reduce emissions and noise, improve airlines' gate-to-gate efficiency, and help meet other environmental goals. The ecoDemonstrator's origins dated to Boeing's Quiet Technology Demonstrator program. The company worked with Rolls-Royce in 2001 to develop a quieter turbofan engine incorporating sawtooth chevrons on the aft end of the nacelle and exhaust nozzle. Additional testing in 2005 allowed designers to refine the chevron design and validate an acoustically treated inlet. Boeing applied these technologies to both the 747-8 and 787, providing dramatic noise reduction. Building on this success, the company began the ecoDemonstrator program in 2011, in cooperation with American Airlines and the FAA. The EAR efforts, which had begun as a partnership among Boeing, the Federal Aviation Administration's Clean, and American Airlines, expanded over time to include Japan Airlines, NASA, Rolls-Royce, General Electric, Rockwell Collins, Honeywell, Panasonic, Stiefel Bank and the TUI Group. Flight evaluations were undertaken with both ecoDemonstrator 737 and 787 jetliners. It was hoped that technologies and processes validated by ecoDemonstrator evaluation would be then incorporated into existing production models and made available for in-service fleets as well as new airplane development programs, supporting long-term sustainable aviation growth. In 2012, the ecoDemonstrator program began with a Boeing 737-800 and 897NN loan from American Airlines, demonstrating 15 advanced technologies, including a variable area fan nozzle, active engine vibration control, flight trajectory optimization, a regenerative hydrogen fuel cell, blended biofuel, and carpet made from recycled materials. Most impressively, it validated the aerodynamic performance of an NLF winglet that improved fuel efficiency by up to 1.8%. In 2014, using an ecoDemonstrator Boeing 787-8 Dreamliner, and 7874, owned by the company, researchers tested a high-strength, heat-resistant ceramic composite nozzle designed to enable jet engines to operate at higher temperatures, improving fuel efficiency while decreasing emissions and noise. Altogether, they evaluated more than 25 new technologies aimed at making airplanes quieter and more fuel efficient. These included aerodynamic and flight control improvements, special coatings to reduce ice accumulation on wing surfaces, and software applications and connectivity technologies for improved flight planning and fuel load optimization. NASA researchers tested a flight interval management system to help achieve precise spacing between aircraft upon landing. Known as Airborne Spacing for Terminal Arrival Routes, ASTAR, this technology is intended to increase landing frequency and reduce holding patterns, thus saving fuel and time and reducing NOx emissions. Toward the end of the year, Boeing demonstrated the world's first flight using green diesel, a sustainable biofuel already widely available and used in ground transportation. For initial testing, the ecoDemonstrator 787 was fueled with a blend of 15% green diesel and 85% petroleum jet fuel in the left engine only. The same blend was later used in both engines on subsequent test flights. Boeing offered data generated by these flights to support industry approval of green diesel for commercial aviation. Other technologies tested on the ecoDemonstrator 787 included touchscreen displays in the flight deck and outer wing access doors made from recycled 787 carbon fiber material. Boeing researchers also introduced wireless sensors in an effort to reduce the amount of wiring in the airplane. 5 The ecoDemonstrator program in 2015. The ecoDemonstrator program tested more than 15 technologies on a modified 757-222, and 757 that had been retired after years of service with United Airlines, and which was owned by Stifel Bank's Finance Group. Project collaborators included the NASA ERA project and the Europe-based TUI Group, an integrated tourism consortium that includes 6 airlines, and which includes the 757 ecoDemonstrator in its fleet. The first series of tests involved Boeing proprietary technologies applied to the airplane's left wing to see if they would reduce environmental effects on natural laminar flow and improve aerodynamic efficiency. During these experiments, high-resolution infrared cameras attached to the top of the fuselage monitored laminar flow over the wing while Boeing test pilots flew the ecoDemonstrator through various environmental conditions to study the potential effects of those conditions on aerodynamics. The most noticeable modification to the airplane was the installation of a 22-foot span variable camber Kruger (VCK) flap designed to protect the leading edge of the wing from insect strikes because insect residue adversely affects airflow over the airfoil surface. Previous attempts to use Kruger flaps as insect mitigation screens resulted in additional drag. To avoid this problem, Boeing's new VCK was designed to retract seamlessly into the lower wing surface. 6 In June 2015, Boeing flew the 757 ecoDemonstrator using a 5% blend of domestically produced green diesel to support ongoing biofuel and aviation industry efforts to have this biofuel approved for use in commercial aviation. Additional Boeing-sponsored demonstrations included solar and thermal energy harvesting to power electronically dimmable windows that would reduce wiring, weight, fuel use, and carbon emissions, and a 3D printed all-stand made from carbon fiber leftover from 787 production, which was an example of the company's efforts to repurpose aerospace-grade carbon fiber and thus reduce both airplane weight and factory waste. 7. Active flow control on a modern multi-engine commercial transport aircraft. The vertical tail is employed primarily to provide directional stability and control at all air speeds across the aircraft's performance envelope. But it is particularly significant during takeoff and landing. A large vertical stabilizer is indispensable in addressing crosswind conditions, as well as in the event of an engine failure that results in the remaining healthy power plants generating unbalancing asymmetrical thrust or torque effects. The vertical stabilizer's size is optimized for low-speed flight, where directional stability and control, the latter via the rudder, is particularly critical. When the aircraft is cruising at altitude, the same large, heavy tail is no longer required. Additionally, designers typically size the vertical tail for the shortest version in an aircraft's model family but use the same tail for every variant to reduce production costs. Thus, the ideal vertical tail for the 777-200 is effectively oversized for the longer 777-300.8. The optimum vertical tail area is determined by the fuselage length/tail moment arm. As this value increases with fuselage length, less tail area is required for stability and control. Sized in this way, the drag and weight of the tail increases fuel consumption for the entire aircraft family. One way to compensate for a reduction in tail size is through the use of active flow control, which is the commanded manipulation of fluid flows with the addition or subtraction of energy from the fluid, in this case, air. By employing AFC technology on the shortest variant of an aircraft family to facilitate both low-speed control and the ability to react to sudden changes in flow conditions, smaller tail sizes may be used on the stretched versions. 9 For the AFC Enhanced Vertical Tail Flight Experiment, NASA worked with Boeing to install dozens of tiny, sweeping jet actuators capable of manipulating, on demand, the airflow over the 757 ecoDemonstrator's vertical tail. This action was calculated to delay flow separation over a highly deflected rudder and to increase the rudder side force capability. If successful, this technology would enable designers to incorporate a smaller vertical tail that provides the necessary control authority during an emergency situation using AFC, while operating in a conventional manner throughout the rest of the flight envelope. Reducing tail size would also lower the airplane's overall airframe weight and aerodynamic drag and decrease fuel consumption. 10 Prior to the ERA project, researchers had demonstrated the capabilities of AFC only on small-scale airplane and component models in laboratory environments. Wind tunnel experiments conducted at Rensselaer Polytechnic Institute in Troy, New York, apply to 8 synthetic jet actuators to a 7% scale vertical stabilizer model, where actuators placed just upstream of the rudder hinge line produced a side force increase of nearly 20% at moderate rudder deflections. Researchers at the California Institute of Technology, Caltech, in Pasadena, California, collaborated with Israel Winiansky, a professor of aerodynamics and fluid mechanics at the University of Arizona, considered the father of active flow control, to install sweeping jet actuators on a 14% scale vertical tail model. In tests carried out using Caltech's 5 by 6 foot Lucas wind tunnel facility, AFC actuation was applied to the rudder and the stabilizer main element's trailing edge. Experiments involving multiple flap deflections and spanwise actuator configurations resulted in a side force increase of as much as 50 to 70% depending on the free stream velocity and momentum input. 11 Installed just beneath the outer skin of the tail along the stabilizer's vertical length, the AFC devices deliver a strong burst of sweeping air just along the rudder, equivalent to the amount of airflow that would normally be encountered by the tail and rudder at higher speeds. Because these jets of air sweep back and forth over the length of the tail rather than blasting a single, linear burst of air, researchers discovered that they could increase airflow over the entire tail with just 6 of the AFC devices. Caltech Aerospace Research Project Manager Emilio Graf suggested that, using such devices, airplane manufacturers could reduce the size of airplane tails by as much as 20%, with the sweeping jet actuators needing to be activated only during takeoff and landing. Fuel savings are derived not only from reduced drag due to the smaller tail size but also from weight savings and structural advantages from having a shorter vertical stabilizer. Even if the AFC system itself used a relatively large amount of energy, it would be activated only for short periods during the takeoff and landing phases of flight. When you take off or land, the air jets will be on, just in case an engine fails, he said, but on a 12-hour flight, if you're only using the system for 30 minutes, you're still saving gas during 11 hours and 30 minutes. 12 Next, as part of NASA's ERA project, Graf and his colleagues designed and built a scaled-up AFC system to test the effects of sweeping jet actuators on a full-sized airliner tail with the help of a multi-institutional team that included engineers from Boeing Research and Technology and NASA LaRC. The test article was an actual 757 vertical tail that had been removed from a retired airliner in storage at Pinal Air Park in Marana, Arizona. With the help of the Boeing test and evaluation team, Advanced Technologies Incorporated, of Newport News, Virginia, modified and refurbished the tail into a wind tunnel model, and installed 31 AFC devices. Because it was nearly 27 feet tall, the next stage of the experiment was moved to the NFAC, one of the world's largest wind tunnels, located at NASA ARC in Mountain View, California. This allowed researchers to realistically simulate wind conditions similar to those that would be experienced during takeoff and landing. 13 The 2-month-long test series began in early September 2013. Data from full-scale testing confirmed that sweeping jet actuators could sufficiently increase the airflow around the rudder to steer the plane in the event of an engine failure. According to Graf, this flow control technique is not new. It has previously been used for augmented takeoffs and landings in military applications. But, he added, existing systems are not energy efficient, and if you need a third engine to power the system, then you may as well use it to fly the plane. By comparison, the AFC system designed by Graf and his colleagues is small and efficient enough to be powered by an airliner's auxiliary power unit, the small engine that powers the cabin's air conditioning and lights at the gate. We were able to prove that a system like this can work at the scale of a commercial airliner, without having to add an extra engine, he said. 14 Sweeping jet actuators were developed more than 50 years ago at the Harry Diamond Research Laboratories, where they were initially considered for use in analog computers and as fluidic amplifiers. Other applications include oscillating windshield washers on cars, shower heads, and irrigation systems that use liquid, mostly water, as the working fluid. Only recently were these devices considered for aeronautical experiments for the purpose of delaying separation on airfoils. They are ideal devices for AFC because they introduce spanwise unsteady, oscillatory blowing with no moving parts, requiring only a steady supply of compressed air. In this sense, the system is similar to steady blowing, but uses less air to provide similar levels of effectiveness. Each actuator is a solid-state unit with no moving parts and an internal feedback loop that causes a continuous jet of air to sweep back and forth across an arc. This action re-energizes the separated flow, reattaching it to the rudder even at higher deflection angles. ERA researchers chose to implement a sweeping jet AFC system on the trailing edge of the main tail element for ease of integration. Successful demonstration served as a major risk reduction step toward a flight demonstration plan for 2015.15. These experiments also provided, for the first time on a commercial aircraft, the opportunity to assess design and scaling issues for full-scale application of AFC and validation of subscale and CFD observations regarding the sensitivity ties and effects of AFC on a vertical tail. The wind tunnel tests enabled the research team to observe a wide array of flow control configurations across the whole low-speed flight envelope of the vertical tail, said Boeing Research and Technology Program Manager Ed Whalen. Based on wind tunnel results, the team selected the most efficient and effective flow control configuration for flight testing on the 757 ecoDemonstrator. According to Fay Collier, the AFC test campaign was a key component of ERA. The maturation of technologies such as active flow control, which will benefit aviation by improving fuel efficiency, reducing emissions and noise levels, is what NASA's aeronautics research is all about, and will have an impact on future green aircraft designs, he said. 16 wind tunnel results demonstrated the effectiveness of AFC jets for increasing side force by 20 to 30%, which would allow aircraft designers to scale down the vertical tail of a 757 class commercial transport by at least 17% and reduce fuel usage by as much as 0.5%. 17 This technology promised other potential benefits as well. In addition to reduced airframe weight and improved fuel economy, this type of device could also allow future aircraft to use shorter runways, or perhaps no runways at all. We can possibly take off from a football field-sized area with some sort of rotor-type airplane, maybe a tilt rotor, and we can fly at maybe 300 to 350 knots, and do this very efficiently, said Israel Wynyansky. If we do it from downtown to downtown, from a parking lot, then that's much more effective than to do it the way we do today, from airport to airport, because you spend so much time in the airports. He added, there are also a lot of smaller airports with runways of less than 5,000 feet that are closer to city centers that can be used, so some sort of short takeoff airplane that can use this technology would be very effective. 18 Now it was time to validate much of the research data in flight. This phase of testing had three primary objectives. First, demonstrate the team's ability to integrate a prototype AFC system into an airframe and thereby highlight key integration challenges. Second, demonstrate AFC impact on rudder effectiveness in flight using available APU flow rates. And, finally, collect in-flight data for comparison to full-scale wind tunnel results and CFD predictions. To meet these objectives, planners outlined a number of system design requirements. These included minimal modifications to existing structures and systems and minimal relocation of flight-critical systems. All installation of test equipment had to be accommodated within the 757's tail assembly. The airplane's auxiliary power unit, APU, powered the AFC system's sweeping jets. APU compressor air temperatures had to be kept below 130 degrees Fahrenheit to protect the integrity of the rudder skin. All externally mounted components had to be bonded in such a way as to mitigate static electricity and electromagnetic emissions risks. In order to power the AFC system, the APU had to be disconnected from the airplane's pneumatic bleed air system, which meant it was not available for starting the engines nor could it provide bleed air for the air conditioning packs. Once AFC testing was completed, the airplane's bleed air system was restored to its original production configuration. 19 Following completion of testing in FAC, the modified tail was installed on the 757 ecoDemonstrator, and testing continued at Boeing Field in Seattle. Integrating AFC system hardware was challenging because the airplane had already been built. Ducting inside the vertical fin had to be installed in multiple segments due to limited access and bends and branches needed to fit within the existing geometry to minimize cutting any part of the aircraft structure. If the system were installed in a new airplane design, designers could incorporate longer tubes and better optimized flow paths, thus reducing both install time and the number of coupling adapters. In addition to routing the plumbing around structures, it was also necessary to mitigate interference with existing systems. Pressurized air, supplied by the APU, was pre-cooled from its 380-degree exit temperature by running it through an externally mounted heat exchanger beneath the aft fuselage. The heat exchanger itself was taken from the 757's original environmental control system and plumbed into a duct running along both the front and rear spars of the stabilizer to ensure an even supply of air to the actuators. In addition, a special duct was calibrated to provide engineers with a primary means of calculating system mass flow. Pressure and temperature sensors installed at key locations allowed researchers to monitor system performance and provided a means to detect a system leak or duct burst. Boeing engineers also had to conduct thorough design and stress analyses to ensure that the new ducting would be able to withstand maximum loading during flight without leakage and be able to accommodate thermal expansion due to the heated APU air. Loads analysis ensured the vertical tail would be able to withstand the additional weight of the ducting and side forces generated during testing. 20 Prior to the first flight, in March 2015, Boeing conducted a series of laboratory and ground tests to verify the overall functionality of the heat exchanger, system controller, and AFC system. Company technicians also conducted a ground vibration test to establish the heat exchanger's frequency response and vibration level limitations. Since many ducting joints were required, technicians performed periodic leak checks at key points during installation to ensure proper sealing. As leaks were discovered, they took appropriate corrective actions until the leak stopped. After the AFC system assembly was fully integrated into the aircraft, a system leak check was completed with no further concerns. This disciplined approach saved time by eliminating the need to chase leaks after installation had been completed, when access to repairs would have been much more difficult. Finally, Boeing completed a total system functionality check that included measuring AFC actuator output and flow output from the Sweeping Jet Actuators. This also ensured that the AFC system was controllable, instrumentation operated nominally, and the system operation process was established. 21 The AFC system, mounted on the right side of the fin only for the tests, comprised 31 Sweeping Jet Actuators positioned ahead of the rudder's leading edge. Then FAC experiments employed 37, but those closest to the tip of the tail proved less effective than desired, according to Doug Christensen, Boeing's ecoDemonstrator program manager. The airplane was equipped with two Pratt & Whitney PW2037 engines leased from Delta Airlines. To maximize the asymmetric forces on the rudder, Boeing modified the left engine via service bulletin to increase the available thrust from 37,000 to 40,000 pounds. The ecoDemonstrator flew test flights with and without the AFC system operating. The rudder was fully instrumented so engineers could determine rudder hinge moments and see how much force was being generated. Chase pilots observed flow cones fixed to the rudder to see how much of the flow remained attached to the rudder. 22 The flight conditions that were necessary to demonstrate AFC effectiveness necessitated that all testing be performed over water under visual flight rules, VFR, conditions. Mission planners, therefore, selected a work area above the Strait of Juan de Fuca, a nearby body of water separating the state of Washington from Vancouver Island, British Columbia, Canada. This site was chosen based on proximity, meteorological analysis of historical weather patterns, cost-effectiveness for flight crew and test monitors, and compatibility and availability of the chase plane for flow visualization photography. 23 After 4 days of AFC flight testing were completed, comprising 6 flights during which the crew performed various maneuvers to evaluate the effectiveness of the AFC jets. Maneuvers included simulated engine failures and variations in AFC jet arrangements and flow rates. According to Gene Yu, Environmental Performance Director for Boeing Commercial Airplanes, these experiments were important for moving the technology forward, and because of the significant savings the technology may potentially afford aircraft operators and the flying public. When you think about the worldwide fleet of airplanes, there are about 18,000 that fly today, and that's projected to increase to about 36,000 airplanes in the next 20 years, you said. If you can get a little bit of improvement on one airplane and multiply it by 36,000 in the next 20 years, it's a huge improvement with regard to reducing overall fuel burn. 24 Active and laminar flow control are NASA's two main areas of investigation for reducing skin friction, which accounts for an estimated 48% of the drag on current airliner designs. The intent is to increase its laminar flow control systems technology readiness level so that it could be applied to any generic wide-body or single-hull hinged rudder, said Tony Washburn, NASA's ERA chief technologist. In the near term, successful results of AFC flight testing could be applied to development of a drag-reducing hybrid laminar flow control system for Boeing's Stretch 787 to 9.25 insect accretion mitigation. The second ERA technology maturation task involving the 757 ecoDemonstrator was the insect accretion mitigation (IAM) experiment. Studies have shown that keeping the airflow smooth, or laminar, over a wing can reduce fuel consumption by roughly 5 to 6%, on average. Among the major challenges to maintaining laminar flow over wing surfaces is roughness induced by insect contamination. Even something as seemingly inconsequential as bug remains spattered on a wing's leading edge can cause turbulent wedges that interrupt laminar flow, resulting in an increase in both drag and fuel consumption. The IAM research effort involved an investigation of insect protection coating technologies for mitigating wing and leading edge insect residue adhesion in order to enhance and maintain natural laminar flow over the ecoDemonstrator's right wing. 26 Success depended on consultation with entomologists and extensive study of bug chemistry, and analysis of what happens when an insect strikes a sore face at a high velocity. We learned when a bug hits and its body ruptures, the blood starts undergoing some chemical changes to make it stickier, said Mia Sayochi, senior materials scientist at Langley. Then the materials scientists turned to nature, specifically, lotus leaves, to create the right combination of chemicals and surface roughness for the test coatings. When you look at a lotus leaf under the microscope, the reason water doesn't stick to it is because it has these rough features that are pointy, said Sayochi. When liquid sits on the microscopically rough leaf surface, the surface tension keeps it from spreading out, so it rolls off, she added. We're trying to use that principle in combina tie-in with chemistry to prevent bugs from sticking. 27 During ERA Phase 1, NASA engineers developed and tested more than 200 non-stick coating formulations at LaRC. Initial testing used a small wind tunnel to propel insects onto a simulated wing leading edge at approximately 150 miles per hour. Coating performance success criteria were based on the insect residue coverage area as measured by profilometry, a quantification of surface roughness. Researchers exposed potential IM coating samples to sunlight and weather to measure durability and the effects of ultraviolet radiation. They then conducted another low-speed wind tunnel test in the LaRC Basic Aerodynamic Research Tunnel, BART, to further down-select the final coatings for flight testing. Following the BART test, an assortment of coatings were affixed to the wing of a NASA Dassault HU-25C Guardian Falcon, a militarized Falcon business jet formerly used by the Coast Guard as a maritime patrol airplane, for a short series of low-altitude flight tests. Based upon the results, the 5 most promising candidates were chosen for use in the 757 ecoDemonstrator IM flight demonstration. 28 The next step was to select a bug-infested area in which to flight test the treated surfaces, and that met the NASA-defined insect density criterion of 25 strikes per square foot. Because insect life is rarely a factor above 10,000 feet, the 757 would have to be flown at low level in a bug-infested area. Researchers installed high-definition cameras in the airplane's forward cabin to view the test sections on the wing through optically clear windows and record the number and size of the insect strikes during each flight. In order to determine the best location for carrying out the experiment, test planners listed all airports capable of handling a 757 around the country, and then matched this with information from entomologists about insect breeding and migration patterns. 29 A team that included members from NASA, Boeing, University of California Davis, and the Department of Transportation's Volpe National Transportation Systems Center narrowed a list of 86 airports in 15 states to 6 airports in 3 states. Eventually, Shreveport Regional Airport in Louisiana was chosen due to a combination of temperature, geology, runway length, and the potential for large numbers of insects. To capture insect accumulation rates, initial test flights established a baseline using uncoated surfaces. Researchers then installed 8 panels treated with samples of each of the coatings onto the ecoDemonstrator's second and third leading edge slats. Among the engineering goals was to test how durable the coatings were. Treated surfaces will be effective as drag reducers only if they can withstand the harsh flying environment. Any degradation of the coatings will result in excess drag. 30 The 5 anti-adhesion surface treatments chosen for the final evaluation were sprayed in a 0.012-inch thick layer onto substrate panels made from 27 by 30-inch 7075 T6 clad aluminum panels. Researchers call this combination an engineered surface, or S, panel. These S panels were positioned on the wing edge adjacent to accompanying control test articles, which were substrate panels without coatings. Researchers arranged the S and control panels in an alternating pattern along slats 8 and 9 on the right wing of the ecoDemonstrator. Prior to flight, Boeing conducted a series of spray tests to develop and verify application procedures. These were done to address specific concerns and questions regarding material quantities needed for producing the coated panels for the flight test, mixing and application protocols to produce consistent and uniform coatings, application tools and methods, and cure rates. Lessons learned from these spray tests ensured the successful application of IM coatings to the 37 S panels used in the flight demonstration. 31 As part of the evaluation, Boeing conducted a trade study to determine the optimum method for attaching the S and control panels to the wing slat's outer surface. The best solution involved applying double-sided adhesive tape to the backside of the aluminum substrate panel. This tape demonstrated sufficiently low adhesion strength to allow for removal of the substrate without deforming the plastic coating, yet was strong enough to withstand aerodynamic loading during flight. This allowed the experimental panels to be removed without degrading insect residue data. The tape also had to withstand exposure to solar radiation and temperature variations. A small piece of copper tape on each panel satisfied grounding requirements for mitigating static electricity generated by the striking of rain, snow, hail, dust, or other atmospheric particles on the airplane surface. Technicians also sealed the edges of the S panels with tape to prevent edge peeling due to aerodynamic forces. During S installation procedural development, researchers noticed some amount of lower surface creep and debonding from the slat surface resulting from the stiffness of the substrate panel. To alleviate this, they added a 2-inch strip of high-strength double-sided, pressure-sensitive adhesive tape. Because this portion of the panel was not subject to insect accretion, some plastic deformation during removal was acceptable. 32 test planners selected flight profiles so as to maximize insect accretion while flying a variety of takeoff conditions to simulate actual airline operations. To achieve a range of climb rates and speeds, the flight crew performed takeoffs at a range of trailing edge flap angles. The leading edge Kruger flaps on both wings were fully deployed and were not retracted during these tests. A total of 15 IM test flights were conducted to maximum altitudes of between 1,500 and 10,000 feet. Selected crew members aboard the 757 ecoDemonstrator monitored onboard camera data during each flight, recording insect accretion counts by panel and slat zone. A 1 square foot template was used to aid in the counting to ensure that each test run met an insect density criterion of 25 strikes per square foot, though this device proved difficult to use. Markings on the uncoated substrate panels split each into equivalent frontal area zones to assist onboard accumulation monitoring. 33 Ultimately, NASA and Boeing created a new assessment process for counting the number of insect strikes in zones 2 and 3, and changed the insect density criterion from 25 strikes per square foot to a total count between 53 to 62 hits in both zones per panel. This process reduced the time needed to confirm the density count. During periodic pauses between test runs, with the flight crew still on board, NASA and Boeing researchers on the ground verified whether the insect strike density on the IM control panels had been met. If not, the flight crew conducted additional sorties until onboard data indicated the density criterion was met before returning to Shreveport. Afterward, all of the S and control panels were photographed, underwent an in situ accretion count, and were removed from the slats before being delivered to La RC for a detailed insect count. In addition, an entomologist identified the various insects that had impacted the panels. Of the 5 different surface treatment coatings, the best, IAMP 5B, demonstrated up to a 37% average reduction in insect accretion over the control panels. 34 The research team was very happy with the results, as insect accretion meant drag and drag meant higher fuel burn. In the complex world of aircraft operations, with billions of passengers flying in jetliners each year, saving even a small percentage of fuel burn adds up to massive savings in operating costs and, more important still, reduces harmful emissions that threaten the environment. This has been about a 5-year effort. We started in the lab, knowing that the problem is that when bugs stick to aircraft wings it affects laminar flow and fuel efficiency, said Mia Sayuchi. We've taken samples of over 200 different compositions from the lab to wind tunnel tests to flying the best 5 on an actual aircraft. If at least one of those works in practical application, where we have significantly reduced the number of bugs sticking to the surface in critical locations where they affect the flow, then this has been a success. 35 Following completion of the 757 ecoDemonstrator program in August 2015, the airplane met an unusual fate for an experimental test bed. Boeing collaborated with Stiefel Bank's Aircraft Finance Division, which owned the airplane, as well as with the Aircraft Fleet Recycling Association and an airplane demolition company in Spokane, Washington, to dismantle and recycle the 757 using environmental best practices. Including parts and materials, about 90% of the airplane by weight was reused or recycled, with only 10% being disposed of in a landfill. 36 This was entirely in keeping with the project's theme of environmental responsibility. The airplane flew to Moses Lake Airport in Washington, where technicians from Aircraft Demolition, LLC, demolished it with an industrial excavator while Boeing engineers and members of the news media watched. Boeing participated in order to study more efficient recycling techniques and determine how to extract the most value from materials and parts on future airplanes. The demolition company removed valuable parts from the airframe and sold them for Stiefel Bank. Included were such items as landing gear, avionics, lavatories, and ductwork, and high-value metals. Many of the components were overhauled, recertified, and returned to service. We are using this opportunity to look at how we can design our airplanes better in the future for end-of-service recycling, said Jean Yu. Watching this has given us insight about using better materials to build the airplane, with recycling in mind, or better design that allows the airplane to be disassembled easier. 37 After 2 months of extracting valuable components, all that remained was recyclable aluminum and unusable material. All of the aluminum scrap went to a company in Tacoma, Washington, where it was sold for reuse in Asia and elsewhere. Boeing engineers used the opportunity to evaluate how more of the airplane-grade aluminum might be recycled for use in future aircraft. Designing for producibility and safety have always been high priorities as we draw up our next new airplane, said Mike Sinnott, Boeing Commercial Airplanes Vice President for Product Development. The ecoDemonstrator program is showing us that looking at the end of service of an airplane should be a consideration also to create higher residual value, economically and environmentally. 38.